Our planet is a world of blue. From space it shimmers, a beautiful azure marble dominated by water. The oceans cover more than 70% of Earth's surface. A single interconnected body of salt water dictates our climate, shapes our coastlines, holds the greatest diversity of life, a realm of immense power and profound mystery. Humans have explored more of the moon than the ocean depths. We've mapped distant stars. What lies beneath the waves remains largely a secret, a three-dimensional world. Towering mountain ranges, deep canyons, sprawling plains, average depth nearly 4 kilometers, into darkness. Strange and wonderful creatures thrive. Ecosystems work in ways we're only beginning to understand. Geological forces reshape the crust, a world older than us, holding keys to our past and future. So what is this science we call oceanography? It is the story of the ocean. It is the study of everything about the sea, from the smallest microscopic organisms to the largest ocean basins. Think of it as being a detective for the marine world. An oceanographer asks questions. Why is the sea salty? What creates the waves? Where do the currents travel? What lives in the deepest, darkest trenches? And how do all these different pieces fit together to create the living, breathing system that is our global ocean? It is a science that seeks to understand the ocean's past, observe its present, and predict its future. Oceanography is not just one single field of study, it is a grand, interdisciplinary science. Much like the ocean itself, is a complex system of interconnected parts. To make it easier to understand, scientists have divided it into 4 main branches. Biological oceanography, which studies marine life. Chemical oceanography, which examines the water's composition. Physical oceanography, which looks at the movement of the ocean such as waves, tides, and currents. And geological oceanography, which explores the seafloor and the processes that shape it. Together, these 4 pillars provide a comprehensive picture of the ocean's character. You cannot fully understand one without having some knowledge of the others. It is like trying to understand a forest by looking only at the trees. The first branch, biological oceanography, is the study of life in the sea. It explores the incredible diversity of organisms, single-celled plankton blue whale. These scientists investigate how marine creatures interact with each other and with their environment. They map out food webs, track migrations, study life cycles. For a seafarer, this is not just about appreciating a pod of dolphins leaping alongside the bow. It's about practical implications. Consider bioluminescence. Ghostly light produced by living organisms, magical at night but also a navigational clue. Wartime sailors recognized glowing wakes from disturbed plankton. Today, bright bioluminescent blooms can indicate nutrient-rich waters or upwellings. Biological oceanography is crucial for the world's fishing fleets. Knowing where fish congregate is the key to a successful catch. Upwelling brings nutrient-rich water to the surface, supporting vast blooms of plankton, which attracts small fish which then attract larger predatory fish like tuna. Even the fouling of a ship's hull, the buildup of marine organisms like barnacles algae. This biofouling can increase a ship's drag, forcing it to burn more fuel and increase costs and emissions. Chemical oceanography delves into the very substance of the ocean, the water itself. It is the study of the chemical composition of seawater and how it varies from place to place and over time. Seawater is not just H2O, it is a complex cocktail of dissolved salts, gases, nutrients, trace elements. A chemical oceanographer might study salinity, or the levels of dissolved oxygen. They also track pollutants like oil or chemical spills, and study their devastating journey through the marine environment. For seafarers, this chemistry has very real and immediate consequences. One of the most direct applications for a ship's crew is understanding corrosion. Salt water is notoriously corrosive, relentlessly eating away at a ship's steel hull, its machinery, its equipment. The rate of this corrosion can change depending on the water's temperature, salinity, and oxygen levels. A ship sailing in warm, highly saline tropical waters will face a greater corrosion challenge than one in the cold, less saline waters of the Arctic. Understanding these chemical principles helps crews implement the right maintenance procedures, apply the correct protective coatings, and anticipate where rust is most likely to form. The chemistry of the ocean also plays a critical role in safety, especially in the event of an accident. If a chemical tanker has a spill, it is the chemical oceanographers who can predict how the substance will behave. Will it float on the surface? Will it dissolve in the water column? Or will it sink to the seafloor? The answers to these questions are vital for the crew of the damaged vessel and for the response teams. Furthermore, new regulations from the International Maritime Organization place strict limits on sulfur content of fuel oils. This has led to widespread use of exhaust gas cleaning systems, or scrubbers. Crews must understand how these systems work and monitor the water they release back into the sea. In this way, the chemistry of the ocean has found its way directly into the engine room. Physical oceanography is the study of the ocean in motion. It examines the forces that stir the great mass of water, from the gentle lapping of waves on a beach to the immense globe-spanning ocean currents. Tides, waves, currents, and the way the ocean interacts with the atmosphere to create our weather. For any seafarer, this branch of science is perhaps the most immediately and consistently relevant to their daily work. Navigating a ship is, in essence, a constant negotiation with the physics of the sea. It's really about working with its movements, not against them. Tides, the daily rise and fall of sea level, are a primary concern. They are caused by the gravitational pull of the moon and the sun. A navigator must know the tidal range in a port to ensure their vessel has enough water beneath its keel when docking or passing through a shallow channel. Miscalculating the tide could lead to a catastrophic grounding, leaving a massive ship stranded. Tidal currents, the horizontal flow of water associated with the tides, can also be incredibly powerful, pushing a ship off course, making maneuvering in tight spaces extremely difficult. Beyond the predictable rhythm of the tides, there are the ocean currents. These are like great rivers flowing within the sea, some on the surface, others in the deep. Gulf Stream Kuroshio. These currents move vast quantities of water and heat around the globe. A ship captain who understands these currents can use them to their advantage. Sailing with a current can save enormous amounts of time and fuel, reducing voyage costs and emissions. Finally, there are the waves. Generated by wind blowing over the water's surface, waves carry energy across entire ocean basins. How they form, how they travel, and how they behave in different conditions. This knowledge is used to create wave forecasts, which are absolutely critical for safety. A captain will use these forecasts to plot a course that avoids the worst of a storm. Beneath the restless surface of the ocean lies another world, the seafloor. Geological oceanography is the study of this hidden landscape. It explores the topography of the ocean floor, from the shallow continental shelves to the abyssal plains and the deep-sea trenches. It also investigates the processes that shape it, such as plate tectonics, underwater volcanoes, sedimentation. For a long time, this underwater world was a complete mystery. Now, thanks to technologies like sonar, we can map it in incredible detail. For the mariner, this hidden geology is of paramount importance. The most direct application of geological oceanography is found in the nautical chart. Every chart a navigator uses is a product of hydrographic surveying. These charts show water depths, the nature of the seabed, whether it is sand, mud, or rock, and the locations of underwater hazards like reefs, wrecks, and rock pinnacles. A navigator relies on this information with absolute trust to plot a safe course. This science is also vital for anchoring. When a ship needs to stop and hold its position, it drops anchor. But the anchor's ability to hold depends entirely on the nature of the seabed. An anchor will dig in and hold firm in soft mud or sand, but it will likely drag or fail to grip on a hard rocky bottom. The nautical chart provides this information, which is derived from geological surveys. Furthermore, geological oceanography helps us understand and prepare for submarine hazards like underwater earthquakes and volcanoes. An earthquake on the seafloor can generate a devastating tsunami, a series of powerful waves that can travel across entire oceans and inundate coastal areas. Understanding the tectonic plates and fault lines where these events are most likely to occur allows for the creation of tsunami warning systems. History is filled with cautionary tales of what happens when ocean science is misunderstood or ignored. These are not just stories, they are powerful lessons written in the language of wrecked hulls and lost lives. One of the most striking examples is the story of the RMS Titanic. While the immediate cause was a collision with an iceberg, a deeper understanding of physical oceanography could have provided a crucial warning. The iceberg that sank the great ship had traveled south from Greenland, carried by the cold, powerful Labrador Current. In the spring of 1912, the conditions were unusual. A milder winter had led to more icebergs breaking off from the glaciers of Greenland. Specific atmospheric conditions had pushed the boundary between the warm Gulf Stream and the cold Labrador Current further south than normal. This effectively created an ice alley that extended directly into the Titanic's path. Experienced mariners of the time were aware of ice seasons, but the science of predicting the exact location and density of ice fields was in its infancy. Another powerful lesson comes from the world of container shipping, specifically concerning a phenomenon known as parametric rolling. This is a complex form of instability that can affect modern wide-beamed container ships. It occurs when the ship is sailing head-on into waves or nearly head-on into waves, and the length of the waves is similar to the length of the ship. This can cause the vessel to roll violently and unpredictably from side to side, sometimes to angles of 30 or 40 degrees. In the early 2000s, several ships experienced severe parametric rolling, leading to massive cargo losses as containers were flung into the sea. Initial investigations were puzzled, as the weather was not exceptionally severe. The answer lay in physical oceanography and naval architecture. It was a specific combination of wave period, wave direction, and ship design that created the dangerous resonance. Crews were not trained to recognize the conditions that led to it, nor did they know how to respond. Today, seafarers are trained to understand this phenomenon. Onboard computers can now warn of the risk. For the men and women who work at sea, oceanography is not an abstract science. It is a toolkit for survival and success. Its importance can be broken down into 4 key areas: safety, navigation, fuel efficiency, crew preparedness. These are not separate issues, they are deeply interconnected. A solid grounding in ocean science enhances them all. It elevates a seafarer from being a mere operator of a vessel to a true mariner, capable of making informed decisions in a complex and often unforgiving environment. First and foremost is safety. Understanding oceanography is fundamental to keeping the crew, the vessel, and the cargo safe. This means using physical oceanography to interpret weather forecasts. It means avoiding the worst of a storm's waves. It means navigating treacherous tidal currents. It means using geological oceanography to read a chart. Second is navigation. Modern navigation is more than just plotting a course on a GPS. It's about executing that course in the most effective way possible. This is where physical oceanography shines. A navigator who understands ocean currents can plan a route that takes advantage of favorable flows. That practice is known as weather routing. This is not just about saving time, it's about a smoother, safer passage. Smart navigation turns the ocean's energy from an obstacle into an ally. Third, and critically in today's world, is fuel efficiency. Fuel is the single largest operating cost for most ships. Smart sailing is green sailing. The era of sailing by instinct alone is over. The modern seafarer must blend traditional seamanship with a firm grasp of science. Oceanography is the bridge between the old ways and the new. It explains why a certain cloud formation predicts a storm. It explains why the water changes color over a shallow bank. It explains why the tide flows stronger in a narrow channel. For the next generation of maritime students and officers, oceanography is essential to their education. It prepares them for a smarter, safer career. As technology advances, so does our ability to see and understand the ocean. Real-time satellite data, sophisticated computer models, a growing network of autonomous sensors. Seafarers will have detailed forecasts at their fingertips, but data is useless without the knowledge to interpret it correctly. Education in oceanography provides context to make sense of the flood of information. It helps seafarers see patterns in the data and make sound decisions that enhance safety and efficiency. The role of the seafarer is evolving, with growing concerns about climate change, ocean health, sustainability. Mariners are on the front lines of stewardship. They are the eyes and ears on the vast, remote oceans. By understanding the science, they can notice changes, report pollution, and operate their vessels to minimize impact. They can become active participants in science, contributing valuable data. Ultimately, the ocean will always hold mysteries, a place of wonder, power, and unpredictability. Through oceanography, we can understand its rhythms, respect its forces, and navigate with greater confidence.